So when we were learning about histograms and PDFs, I told you that. So for example, let's assume we have these six observations, and of course, this is how my histogram will look like, right? From this histogram, I've always told you that histogram from histogram I can compute my PDF by smoothing, but I haven't told you how it is exactly done. It's done using something called kernel density estimation, using a very simple trick called kernel density estimation. And I promised you that I'll discuss how it's exactly done when we learn Gaussian distribution. And here we are trying to understand how to construct a PDF from a histogram. Okay, and for that we will use our bell-shaped curves that we just learned while we were understanding about Gaussian distribution. So let's assume I have six observations: 1, 2, 3, 4, 5, and 6 observations. And this is how the histogram looks, right? So in this region there are more points, in this region there are fewer points, this region there are fewer points, and in these regions there are no points at all. So for this curve, for this distribution of points, this is how the probability density function looks like. This is how my probability density function. You will notice that this is basically a smooth form of what we see here, except that we don't go to zero here. So the way it's constructed is basically building something called kernels. The way it works is as follows. So let's take each of my points here. Let's take this point, my sixth point here, right? I take my sixth point. So I'll construct a simple bell curve here, or a kernel. This is called a kernel here. This is called a Gaussian kernel here. This is called a Gaussian kernel here. What I've done here is I have plotted a Gaussian kernel here, the bell-shaped curve, centered on my sixth point. Similarly, for my fifth point, I've also constructed a Gaussian kernel centered around my fifth point. I've done the same thing with my fourth point, and so on and so forth. Now what I do here is, at any point x now, at any point x here, I sum up the values. So in this case, what I'll do is I'll sum up. So corresponding to x, I have how many of my kernels do I have here? I have 3 kernels here. I'll take this value, I'll take this value, I'll take this value. I'll sum all 3 of them up to get the height of my PDF using kernel density estimation. Similarly, at this point, suppose I want to find what is the height of a point here. So what all kernels do I have? I have this kernel with this height, right? Just perpendicular to my x-axis. I have this kernel with this height, I have this kernel with this height, and I have this kernel with this height, right? Which means my total height is going to be sum of this height plus this height plus this height plus this height, which will be here, right? So that's how. So this is called kernel density estimation, wherein I'm drawing Gaussian kernels here. I'm basically drawing Gaussian kernels here. Of course, the next question is, you said that the mean is around this point, around each of my observations. What about variance? Okay, the variance in kernel estimation, this variance is also called as bandwidth. You remember when we learned about histograms in exploratory data analysis, we said that if we decrease the window size or if we increase the number of bins, the plot becomes very, very jagged like this, right? You remember that example that we saw, that as the number of bins increases, my PDF becomes very jagged, right? Similar properties apply for bandwidth. We'll just see an example in a while. But the idea of constructing, so why is this intuitively right? If there are more points in a neighborhood, so let's assume in this area, right, around this point, there are 2 other points, which means at this point, corresponding to this point, you'll find a lot of densities. For example, you'll find the probability density function of this point itself. You'll also find you'll find the kernel corresponding to this point itself. Since these 2 points are in the proximity of my blue point here, I'll also get very high values of kernel density of my Gaussian kernels here, and all 3 of them will add up to create a very, very large value, right? So if points are crowded here, or if there is a high density of points here, my height will be more. This is one way of smoothing. This is called a kernel density estimation using Gaussian kernels. So these are called Gaussian kernels here, right? Now I told you about variance and how it impacts. The variance in this case is called a bandwidth. So let's take this is a very nice concept here, right? So let's assume, just for simplicity, that this gray line, so that these are my observations, right? My each of these vertical small blue lines here is my observation. Let's assume the gray is the actual distribution. Let's assume the gray is the actual PDF. By distribution, I meant PDF, right? If I choose kernels which are very wide, my PDF will look like my green line. If I choose kernels which are very narrow, right, I'll get a line like my red line, which is again very jagged, just like the way just like our histogram when we had lot of bins, right? So this is small bandwidth. This is very large bandwidth, right? A more optimal bandwidth, if you choose as you change your bandwidth, you'll get a more smoother curve like your black curve, which is a nice approximation of your actual distribution, which is your gray curve here. This is a medium bandwidth, right? So in lot of libraries like Seaborn, there are nice heuristics, nice hacks on how to find the right bandwidth. So intuitively what they do is they choose a very small bandwidth to start with, and they measure how much jagged is this line. And they keep increasing the bandwidth till the time the line becomes smooth enough, but not too flattened out. Right? This is the idea of kernel density estimation using Gaussian kernels.